All right, line R2, we're in learning task number 1, which is going to be identify devices. This is going to be a very code-heavy section that we're going to go through. There's a lot of generalizations that are just kind of talked about inside of the binder over here, but we're going to actually go find those locations inside of the code book. So make sure you're settled in with your code book on the table in front of you, and you've got your highlighter. Second year is very much a single-phase year where we are working at identifying single-phase types of components. And one of those types of components that we need to have is going to be our disconnecting means, as well as we're going to go through then, differences between disconnection and isolation. We're going to go into some of our utilization equipment and splitters and stuff as well. Let's start with the very first one over here, which is going to be disconnecting means. There always needs to be a way to shut power off, both practically from this fact that we don't want to necessarily run stuff, but also from that whole point of safety, that we need to have that isolation if somebody would be stuck on anything electrical or anything that's mechanical that's powered by electricity, or for us to even be able to go and maintain that. Whenever we're going to do any sort of maintenance or repairs, we have to go and isolate. You are never, ever authorized to go and work on a system live. There's huge amounts of paperwork that need to be done before you're even allowed to, replace a breaker inside of a live panel or replace a switch or anything like that. You're supposed to have written work orders. It's supposed to be provable that it is absolutely impossible for that system to be shut down, etc. And monetary loss is not considered to be an emergency by Technical Safety BC, who mandates the state of safety for electricity in our province. If somebody's saying, well, I'm going to lose money if I got to shut this thing down for a day, doesn't matter. It is not considered to be a safety aspect. The number of lines that we are going to be switching is obviously going to go and determine the number of poles. This is a term that you should be familiar with at this point. We would go and call something that looks like this a single pole switch over here, because it's got a single line that we would be able to run through that. If I have got something that looks like this, we would go and refer to that as a two-pole switch, if these two are going to be tied together so that they operate. This one over here would be referred to as a DP, double pole, and then ST, single throw. We throw it either into the on position or into the off position. Throw is the number of positions that it can have. This one can either be high or low, on or off. So it's a single throw. Double throw would be on, off, on, would be what we would look at. We looked at that stuff inside of our V line, though. We're not going to go back over it. You need to go and have the proper number of lines to go and sever all of your incoming lines. We are not required to switch the neutral. We are allowed to switch the neutral, but only if in doing so, we simultaneously switch everything else off. So you are allowed to run the neutral through a switch, but it's not necessary to run it through a switch. And we can only do it when, once again, it's all tied together. We should never have the capabilities that I could just operate this switch on its own, back and forth like that, without having to, operate these lines as well. Because I would disconnect, you end up with floating neutrals, and if you remember it all back from first year, if you lose your neutral connection, you run into some massive potentials for, unbalanced voltages. We talked a little bit about that this year as well, inside of transformers. Okay, the devices need to be able to go and handle our make and our break currents. There's going to be a difference between making current and breaking current when something's actually running. We're just going to go into 14, and we're just going to roll down here to, just a second, 14400 is where I want to go with this one. It's going to be our make and break ones. 14400 states that control devices shall have ratings suitable for the connected load of the circuit that they control. So they have to be able to carry their continuous amps. And with the exception of an isolating switch, they shall be capable of safely establishing and interrupting such loads. So they have to have make and break ratings unless they're going to be an isolating switch. You might say, well, what exactly is an isolating switch? Very good thing that you asked. We're going to go to section 0, because 0 tells us about that. We're just going to roll all the way through into that. And we'll go down to switches. And almost there. Perfect. Isolating switch. It is a switch designed for isolating either a circuit or some equipment from its source of supply, and that is not intended either for establishing or interrupting the flow of current. So in other words, this would be like that safety switch that you might have on a AC unit on the side of a house. I don't know if you've ever seen those duck boxes. They're one where we have a pull-out switch. It's this little T handle that you pull out. You can flip it around. Obviously, you don't want to be making and breaking running current because the arcing is going to be intense inside there. In fact, they're rated, they say, do not use to switch, current on and off. What you would do is you'd use the breaker to shut that off, and then you would pull the isolating switch, and the isolating switch should not be interrupting current. It's just there to go and prevent the establishing of current if somebody were to go and turn the breaker back on. Let's just quickly draw that out. Over here, the signal of operation. We'll just draw this out here as a circuit breaker. So I've got my breaker over there. We're then going to go and run this thing over to my isolating switch over here. And then we're going to go run that over to my load over there. If I were to go and flip this breaker off, so I'm going to go and disconnect the breaker right now. At that point, then I would be able to go and open my isolating switch. And then I'm safe to go and work on whatever that load is down there. Somebody else could come back in, they could flip that breaker on, but that isolating switch has already got an air gap in between it. So it doesn't need to interrupt current, it's just preventing that current from starting out again. That's the point of the isolating switch. It's just a safety device. We'll go and open this breaker up again. Open it up like that. What we'll do now with the breaker open is we'll close the isolating switch because it's not designed to interrupt or, apply current. And then what we'll do is we will go back here and we will go and close that breaker once again. That's the whole point of that isolating switch. They never, never, never can be operated underneath load. All right, there's a couple other disconnects that they talk about inside of here. Disconnecting means sometimes they're going to have a higher percentage rating as well that we will utilize with them. So if I'm going to be dealing with a capacitor, we need to go and have a circuit that's going to be rated a little bit higher than 100% of what the current would be. We're going to have to go to 135. We're going to go back into our code book here. If you roll into section 26, right near the very beginning of your section 26, there's a whole pile of rules to do with your capacitors. We'll go there right now. 26-200 and on. And if we go down just a little bit over here to disconnecting means that we need one, to the rating of it. The rating of the disconnecting means for a capacitor feeder or branch circuit shall not be less than 135% of the rating that we would need to go and have for that. There is also going to be an overcurrent device that needs to also be provided ahead of your capacitor over there. So you do need to go and place that in there. In most cases, we're going to go with a fusible disconnect. That's going to go and have that overcurrent protection inside there. Note that it says that the overcurrent protection shall not exceed 250%. That doesn't mean it needs to be 250%. I can go and match my overcurrent to 135% as well. The reason that we often have these larger ones is just that instantaneous inrush we get the very first time that we apply power. When we went through all of the A line and we looked at power factor correction, we saw that there is going to be no current that's going to come from the supply to the capacitor while it's operating, but that instant that we turn it on, we do get an inrush. And then once we've stored electrons on the plates, then after that, the inductive and the capacitive loads can just pass them back and forth. For motors, we've got a separate section of the code that we have to go and deal with. We need to go and take a look at, one second. Oh, sorry, we're not going to go into motors here yet. Let's first finish this one up off of these ones here. No, we'll go into the motors there. One second, I just got lost on what I was trying to go onto there. We're going to go to section 28, which is going to be our motors. We're going to go quite a ways through our section 28. And we're going to go all the way down into my control and disconnecting means, which is going to be 28.602. 28.602 talks about my disconnecting means. If I'm going to go and have a circuit breaker, it needs to be rated for 115%. Once again, we are going to be dealing with inrushes that we are going to go and have for a motor off of these things. So just always make sure that they're, once again, going to be a little bit larger. You're going to be following the proper sections of your code. If I'm going to go and have a group of motors, I'm going to be 115% of the full load current on the largest motor plus the sum of the full load currents on all the other motors. Just inrush that we're dealing with over here. The next spot that they talk about is going to be my transformers. Transformers are going to be found back inside of my section 26 as well. We've dealt with these a number of times this year, but 26.248 is where we're going here. 26.248 states that there has to be a disconnecting means in the primary circuit of all transformers. Now, it doesn't say that we need to go and size this thing at 135% or anything like that. It just tells us that we need to have a disconnecting means in there. We're going to base that disconnecting means upon what the actual current is that we are taking through that circuit. So same deal as what we've dealt with before. What you'll note as well is that we do not require overcurrent protection, though, necessarily inside of that disconnecting means. Transformer overcurrent protection can be on either the primary, the incoming power side, or on the secondary, the outgoing power side. Usually, we do see it on the primary side because, I mean, we're having to place in the disconnect at this point, and so we might as well go and get ourselves a fusible disconnect, right? We can get a disconnect that looks like this, that's just got lugs inside of it, or we can get a fusible disconnect that has got lugs in the spot for the breaker inside of it. Inside of your code book, you should have also already done those highlights off of your table 13 for your standard sizes. They talk about them inside of the binder over here, but your table 13, we did go over top of this one earlier this year. I'm just going to roll to it one more time, just in case you haven't yet done that. Make sure that you have got these highlights in here that are going to be your standard fusible disconnect size. The 30, the 60, the 100, 200, 400, 600, and the 800. Those are going to be our standard cases that we are going to have inside of here. Breakers are going to be available inside of any of these ones. So any of these overcurrent devices over here are available as breakers or breaker settings, as well as fuses, including this 25 amp. The 25 amp is a special one. We don't see a lot of it, but it's actually really handy for dealing with baseboard heating because we can use number 14 gauge wire, but we can load that thing up to 4,500 watts of heat off of it. There are some switches that we are not allowed to go and utilize as disconnecting means. The book talks about this inside of here, that it says, you know, we cannot be using two-way and three-way, three-way and four-way switches to do any sort of disconnecting means, just because there's always going to be a hotline going through that. You'd think that you'd find that under your section on protection and control, but it's actually a Section 2 rule. Section 2 is our original code book, so it's a small one. It's kind of a generalized one. I'm going to roll over to 2304 over here. It says 3- or 4-way switches shall not be considered as being a disconnecting means. We're not allowed to use them as a disconnecting means if we're going to work on something. Obviously, the 4-way is just flipping the lines around. 3-way is always going to have one. And you'll notice well over here what we said before, no repairs or alterations shall be carried out on any live equipment except where complete disconnection of that equipment is not feasible. If we go to our Appendix B on there, are the only things where complete disconnection are not feasible is going to be troubleshooting of control circuits, testing and diagnostics. Obviously where you need to go and have the power on to go and run a meter off of this thing. All right. Going back into our binder then, that's most of our isolation one. There is another little section here dealing with isolation inside of section 14. 14 is going to be protection and control. We call this thing P&C, and if I go all the way down into P&C at the very end over here, it talks about solid state devices. We talked about this inside of electronics, that you cannot go and use a solid state device as an isolating switch or as a disconnecting means. Big reason for this was once again going to be that we have got that leakage current through it. What are solid state devices? The most common ones you will run into are going to be the dimmer switches, electronic dimmer switches. You can never trust one of those as being your disconnecting means if you are going to go and work on anything. Okay. Going back into our module then again, they move on into the capacitors, which is another one of the ITA mandated devices for you to identify. These are going to be power factor correction capacitors. I don't know why this picture is so blurry, but that's what they look like. They're going to be big squares. They usually have got these little tabs on the bottom that we're going to be able to do some mounting with. And then we're going to go and have our bushings on the top. This is what we refer to as an electrical bushing, and it's going to be a high voltage connection point onto these. These will be even on medium ones, you know, just because of the way that they construct these things. You need to have some sort of a sturdy lug for you to go mount onto these things. They do talk about, you know, that we don't need to, or we should not go and exceed the ratings off of them, the AC as well as the DC working voltage. We've calculated DC working voltages by taking our AC and taking it to a peak before. Make sure that whatever caps you're going to be utilizing are rated for that. And then the next bit is a set of calculations where they go through and they say, hey, what would happen if I use a cap that is rated for a different frequency? So they have a cap that is going to be a 60 hertz cap that they're going to use on a 50 hertz supply. That's the example that's given inside of there. I'm not a particularly big fan of that example because when I take a look at it, I don't have 50 hertz systems. Here in North America, we are running a 60 hertz system. So it is more common for this to be happening in the opposite way, where we might go and have our 60 hertz system, but what we've bought is a 50 hertz cap that we are going to be utilizing. If we buy that 50 hertz capacitor and we try to use it on our 60 hertz system, we are going to go and have an increase in our number of VARs. If this thing was rated before at 10 kVARs, what we are going to go and see is we are going to go and see an increase. You can go through all the steps and do that calculation. You should be familiar with it. I'm not going to go through those again because that was A1 materials, but you can use the same steps as they show inside of the book, but go in the opposite direction. Take a 60 hertz cap and work that thing, take a 50 hertz cap and work that thing onto a 60 hertz system, because you will at times run into European or Asian equipment that is designed for a 50 hertz system that is then going to be placed onto a 60 hertz, and it changes all the values inside there. There are rules to do with our capacitors that are all going to be found inside of section 26. We talked about the disconnecting means inside of section 26, but if I go into my 26200 and beyond 26200 all the way through deals with, when I install them indoors, the guarding of them, the grounding of them, conductor sizing for them. You'll note that the conductor sizing has to be 135% as well. It's going to go and match what we have for that disconnecting means that we are going to have. We do need to have a disconnecting means within sight of and within 9 meters of our capacitors. Unless we can lock the disconnecting means in the open position, then it's allowed to be further away. And we have to go and have a warning notice shall be affixed to the disconnecting means on your capacitor, stating that the circuit has capacitors and a waiting period of 5 minutes is necessary when the circuit is open, after which the capacitors shall be discharged before handling. And then if I go down into my contactors have to be rated once again to handle that inrush, unless they're an enclosed type of contactor. Enclosed contactor is going to have a bigger they just have to be a bit more robust, because what we have is a sealed contactor, which means that all of that thermal energy, the arc that we are going to get, needs to be contained inside of that. And so we have to have just a stronger rated contactor, so we have to bring them up to 150%. Motor circuit capacitors, this is just going to be dealing with the individual motors. It just states that we don't need to have an individual disconnecting means for the capacitor if it's on with the motor itself. We can go and stick that things together. Transformers, once again, if I got a transformer that's going to supply a cap, has to be rated for that 135%. And then this really, really big one, that all caps have to be provided with that means of draining the stored charge. We are always looking to go and knock that down to 50 volts or less. And if it's a low voltage, it should only take a 1 minute time period. If it's a high voltage, it is going to go and take 5 minutes. Okay, that's the caps. Let's go into our splitters. Splitters are going to be a section 14 thing. And if I roll into my section 14 gives me a bunch of general protection and control, and then it's got this really big rule to us called the 14100 overcurrent protection of conductors over here. That's what they're talking about in that very first paragraph inside of the splitters over there, where they're saying, each ungrounded conductor shall be protected by an overcurrent device at the point where it receives its supply of current. So wherever we give current to a conductor, we should have a breaker or a fuse on it. And we need to go and have an overcurrent device at each point where the size of the conductor is decreased. That would make sense as well, right? So a smaller conductor, we need to go and downsize the overcurrent as well. And then it says, except that such protection, so the overcurrent, shall be permitted to be omitted in each of the following cases. And then it gives us 3 main cases and then a bunch of smaller, lesser used cases. Let's talk about the three main cases over here, because these are very, very applicable to us as electricians. What we should have on number 1 it says that we don't need to have a breaker where the overcurrent device in the larger current properly protects the smaller conductor. What this would be talking about is where I might have upsized my conductors. So where I'm going to go and have a 200 amp breaker, let's say, and that 200 amp breaker is going to be feeding out a long distance to another component. And I might have upped this thing. Normally I'd be running 250s, but maybe I ran this thing all the way up to 500 kc mil at this point. If this is a 500 kc mil, I need to then go and terminate it onto a smaller set of conductors over here that are going to be my 250s, because I'm going to need to have those 250s going into my actual, device, my 200 amp rated, we'll call it a panel that we have over here. This is going to be difficult to do with the 500 kc mils, so I'm going to have to drop back down. That's where this 0.1 comes in, is that we don't need to go and have a breaker over here because my 250 kc mil is rated for that 200 amps already that's going to be on it. So we do not need it in this situation. That's going to be number one over there. The next one is we don't need to have an overcurrent device where the smaller conductor has an ampacity not less than the combined computed loads of the circuits and is not less than the ampere rating of the switchboard, panel board, or control device supplied by the smaller conductor. So this implies that my conductor has to go into a panel, a switch, or a control device, and it's not over top, over 3 meters long, and it does not extend beyond the switchboard, panel board, or control device that it supplies. Looking at that over here, that would be my Subrule B, so we'll draw this one out. This would be if I have got a splitter, and maybe feeding into the splitter, I'm going to go and have, we'll call this thing 400 amps. Then dropping out of that splitter, I've got a whole pile of smaller disconnects. Now, if I've got 400 amp wires, that's going to be twinned up 250s that we're going to be running into this thing. But let's say I've got a 30 amp switch that I need to go and feed out of that. Okay, I've got some sort of a load. Maybe the load is about 20-ish amps. So I'm going to go feed that out of a 30 amp switch because that's going to be my next standard size. What I'm allowed to do is I'm allowed to take 30 amp wire, write that right next to that one there. I'm allowed to go and use 30 amp wire and run that down from here. As long as my switch is 30 amps, I can use the 30 amp wire. It's rated to that. I just have to keep this thing underneath 3 meters long. Really handy. We then do have inside of this overcurrent device, it's a switch. It talks about switchboards, panel boards, and control devices. Inside of here is then where I would go and place my next set of fuses that would then protect the rest of the conductor going out to, whatever it is. Maybe it's a rooftop unit or something like that. The next one down is going to be Subrule C. Subrule C says I don't need to have a breaker at the point where I drop my conductor size, as long as the conductor has an ampacity that is not less than a third and it's not more than 7.5 meters long. And it's going to go and terminate in a single overcurrent device that's rated set at a value not exceeding the ampacity of the conductor. So going back to this one over here, what that states is that I'm allowed to go further than the 3 meters. So I'm coming off of these 400 amp lugs, and I don't need a breaker on the lugs. I'm just going to come off of these. I'm allowed to go further all the way up to 7.5 meters, provided that whatever I'm running here is going to have an ampacity that's going to be at least a third of this. So a third of 400 amps would be 133 amps. The conductors would have to be 133 amps. I might be taking them in to something over here that would be a 100 amp switch. That wouldn't work. We can't stick 133 amps underneath 100 amp lugs over there. So what I would need to do is I would have to say, well, if I've got to feed out maybe an 80 amp load over here, I'm going to go and have this 200 amp panel, or 200 amp disconnect that I'm going to have, and then I'm going to have to run 200 amp conductors into that 200 amp disconnect over there. And then that is going to allow me to then, drop down to the 100 amp fuses that I'm going to have going out from here. We're allowed to do that over 7.5 meters. If I want it though, I could shorten this thing up and take it to just 3 meters. And if I took it to 3 meters, what I'd be able to do for that 80 amp load then is I would be able to go and have a 100 amp disconnect and 100 amp wires. So we get a win whenever we get in tight to my splitters. Anytime we start going further from the splitters, we have to start going to larger and larger conductors. And really what 14100 is trying to do is it's trying to limit the liability, right? The longer the conductor is, the greater the chance that something dumb is going to go and happen to it. You know, somebody runs into it, it gets nailed, screws, you know, driven into it, whatever it's going to be. It just becomes this bigger liability. So they try to keep this stuff in nice and tight. What you do need to be aware of as well, if you ever are laying out these splitters, is always leave room for your tiny, tiny loads tight in. If I had started, you know, I was building my electrical room, and you have to have all the doors, you know, opening out to 90 degrees, etc. And if I did not leave room for this 30 amp switch over here, what could happen is this terrible, terrible thing where, you know, I just can't fit it close. I can't get it within 3 meters of here. I can't get it within 7.5 meters of it. The load was only 20 amp. But if I could not fit that thing tight into there, what I would need to have would be a 400 amp switch with 400 amp conductors coming out of here, because this thing would be over 7.5 meters long. And then I'm feeding a 20 amp load out of a 400 amp switch. Customers, bosses, people are just going to be disgusted if they see this. But if you don't do proper planning, you are going to run into these situations. So if you know what your loads are, what you got to feed out of these splitters, start with your small loads. Make sure that you kind of block out. Don't mount them right away, but just kind of measure up and say, yeah, I'm going to go in place. I got a couple of 30 amp disconnects for some AC stuff. Then I've got 100 amp disconnects, 200 amp disconnects, etc. I would always start with my small ones, tight in, because then I can go small wires to small disconnects for small loads. The next size up, you know, if I've got to go to a 200 amp panel for a 80 amp load, is not as much of a, you know, shock as if I've got to go to a 400 amp, you know, off of a 20. So work your way out. Start with your small ones first. Block off that room, and then move out towards your larger ones. If I have a 400 amp panel that would be coming off of here, I would make sure that I keep that thing well away from here, you know, because I'm going to reserve that room tight to the splitter for my other smaller loads. Okay, there is a thing in your binder here, right above there, the paragraph above, it says a splitter must be used anytime that connection of more than 2 conductors of number 6 or larger is required. This is not true. Sometimes we are required to go and have a splitter just so that we can terminate the proper number of conductors underneath it. But the splitter itself is not the only way. We do have these other insulated lugs that we are going to utilize as well. We call them horticulture lugs. I don't know where the name came from. I don't even know if that name is still, you know, the popular name. Maybe that's changed again as well. But they're these rubber-coated lugs that you can just, you know, tap wires together with. Okay, utilization equipment. The last thing that we're going to talk about is utilization, which is going to be point of user equipment. Anything that is going to be point of user equipment needs to be identified. And the code gives us a pile of rules on identification down in section number 2. Section 2 being our general rules. So we're going to go to 2.100. And it says, each piece of electrical equipment shall bear those of the following. So not all of them, but the necessary ones, to identify the equipment and to ensure it is suitable for the particular installation. We need to go and have the maker's name or other recognized symbol of identification, catalog number, or type. So the name and the model so that we can look up the date on it, see if it's approved, etc. Volts, amps, watts, VA, or horsepower, if it's going to be DC, phasing, frequency, rated speed, designation of terminals, continuous or intermittent duty. So whatever is necessary to identify this thing. For a heater, you know, what you would be looking for would be watts, and you'd be looking for your volts, and then your amps as well. You know, that's the only 3 things that you would need to have on there electrically, obviously not the rest of these ones, and then just the maker's name and number. And usually we're going to see frequency as well. That's going to be on there. All of those things need to be on there. The really big one that we are going to go and have is this one over here, Subrule M, which is going to be evidence of approval. This is going to be the CSA or Intertech or Warner Hersey or whoever it is that has approved it. We need to see that on there. If you go onto the Technical Safety BC and you take a look at, they've got a list of approved certification agencies. It's not just CSA. CSA is probably our most common one, but the list is actually much larger than that. What you do need to know is that this one over here You may have seen this one before. That is not a suitable marking for here in Canada. That is a European marking. Yes, it's got a C in it. I know a lot of times we're like, it's got a C. That must be a Canadian marking. It conforms to European is what it is. It's a kind of a funny-looking C with a funny-looking E over there. You've probably seen it before at some point, but that is not an approved mark here for Canada. So don't be using that one. Okay, and the very last rule that they bring up inside of this section is that all installations need to be done to an acceptable quality of workmanship. We're going to go to that rule because that is the fail-all rule. 2112, quality. The mechanical arrangement and the execution of the work in connection with any electrical installation shall be acceptable. This is the rule that basically allows any inspector to say, I don't really have anything I can fail you on, but this is garbage the way that you've run it. You know, it's just, yes, technically maybe you're correct in the way that you're doing it, but it looks like crap, and I feel like there's, you know, probably other dodgy stuff, so I'm just going to fail the whole thing underneath there. If you're putting out piss poor looking work, they're allowed to fail you off of the fact that it just looks like the dog's breakfast. So don't be, you know, that hack. Make sure you're running stuff proper. I know we want to work fast, but we also want to make sure that the mechanical arrangement, the way that we lay out our cables, the way that we run them, you know, the way we run stuff up holes, or we drill our holes through studs inside of a house or things like that. And then the execution, the sloppiness of it, we just want to make sure that we have this thing done tight, done right, all right? Okay, that is it for the run through here on Learning Task 1. Do make sure you have read through it because I didn't cover absolutely everything that's inside of there, but this is a lot of the code highlights from that content.